Electrical engineering interview questions and answers. Want to crack your electrical engineering interview with confidence? Discover the top 20 most common questions with smart answers that impress recruiters and help you land your dream job. Let's begin. 1. What is Ohm's law and why is it important? Ohm's law is a fundamental principle in electrical engineering that defines the relationship between voltage, V, current, I, and resistance, R, in an electrical circuit. It states that V equals I times R, meaning the voltage across a conductor is directly proportional to the current flowing through it, given constant resistance. This law is crucial because it allows engineers and technicians to calculate and predict how electrical circuits will behave under different conditions. Understanding Ohm's law helps in designing safe and efficient electrical systems, troubleshooting faults, and selecting appropriate components like resistors and power supplies. It's the basis for analyzing both simple and complex circuits, making it an essential concept for students, electricians, and engineers alike. Without Ohm's law, managing electrical systems accurately would be nearly impossible. 2. Can you explain the difference between AC and DC current? AC, alternating current, and DC, direct current, are two types of electrical current used in various applications. DC flows in one constant direction, typically found in batteries, solar cells, and electronic devices. It delivers a steady voltage, making it ideal for low-voltage applications. AC, on the other hand, changes direction periodically, meaning the flow of electrons reverses back and forth. AC is used in household power outlets and large-scale power transmission because it's easier to transport over long distances with less energy loss. Most countries use AC at 50 or 60 Hz frequency. The key difference lies in the flow direction and application. While DC is used for electronics and storage, AC powers homes, industries, and the grid. Understanding both is vital for designing and working with electrical systems effectively. 3. What is the function of a transformer? A transformer is an electrical device used to transfer electrical energy between two or more circuits through electromagnetic induction. Its primary function is to increase, step up, or decrease, step down, voltage levels while maintaining the same frequency. This ability to change voltage levels makes transformers essential in power distribution systems. For example, a step-up transformer increases voltage for efficient long-distance transmission, reducing energy loss. At the receiving end, a step-down transformer lowers the voltage for safe use in homes and businesses. Transformers consist of primary and secondary coils wound around a magnetic core, and the voltage change depends on the ratio of these windings. They are crucial for electrical safety, energy efficiency, and adapting power to meet the needs of different devices and systems. Without transformers, modern power distribution would be inefficient and unsafe. 4. How does a circuit breaker work? A circuit breaker is a safety device designed to protect an electrical circuit from damage caused by overload or short circuit. Its primary function is to automatically interrupt the flow of electricity when it detects a fault condition. When the current flowing through the circuit exceeds the breaker's rated capacity, it trips, opening the circuit and stopping the flow of electricity. This prevents overheating, fire hazards, and damage to appliances. Circuit breakers can be reset manually or automatically, unlike fuses that must be replaced after use. Inside, they use electromagnetic or thermal mechanisms to detect excessive current. Commonly found in residential, commercial, and industrial electrical panels, circuit breakers are essential for electrical safety. They ensure that electrical systems operate within safe limits, protecting both people and equipment from electrical faults or accidents. 5. What is power factor and why does it matter? Power factor is a measure of how effectively electrical power is being used in a system. It is the ratio of real power, kW, which performs useful work, to apparent power, kVA, which is the total power supplied. Power factor values range from 0 to 1, with 1, or 100%, being ideal, meaning all the power is used efficiently. A low power factor indicates poor efficiency, as more power is wasted in the system. This can lead to higher electricity bills, overheating of equipment, and increased strain on the electrical infrastructure. Industries and large facilities often aim to improve power factor using devices like capacitors or synchronous condensers. Maintaining a high power factor is important because it reduces energy losses, improves system capacity, and lowers operational costs, making power systems more reliable and efficient. 6. What are the types of electrical loads? Electrical loads are devices or systems that consume electrical power in a circuit. They can be classified into three main types: resistive, inductive, and capacitive. Resistive loads convert electrical energy directly into heat, such as in electric heaters, incandescent bulbs, and toasters. These have a power factor close to 1, meaning efficient energy use. Inductive loads include motors, transformers, and fans. These devices create a magnetic field, causing current to lag behind voltage, resulting in a lower power factor. Capacitive loads, though less common, include capacitor banks and certain electronic devices. They cause current to lead voltage. Some loads may be combinations, such as air conditioners or washing machines, which are both resistive and inductive. Understanding load types helps in system design, power management, and ensuring efficient and safe operation of electrical circuits. 7. How do you calculate electrical power? Electrical power is the rate at which electrical energy is consumed or transferred in a circuit. It is typically measured in watts, W. The basic formula to calculate power is P equals V times I, where P is power in watts, V is voltage in volts, and I is current in amperes. In AC circuits, especially when dealing with inductive or capacitive loads, the formula becomes P equals V times I times power factor, for real or true power. There are also formulas for resistive circuits using Ohm's law. P equals I squared times R, or P equals V squared divided by R, where R is resistance in ohms. Knowing how to calculate electrical power is essential for designing, analyzing, and safely operating electrical systems, ensuring devices receive the correct power level and avoiding overloading circuits. 8. What are the main components of an electric motor? An electric motor is a device that converts electrical energy into mechanical motion. Its main components include the stator, rotor, commutator, in DC motors, bearings, and housing. The stator is the stationary part that produces a magnetic field, either through permanent magnets or electromagnets. The rotor is the rotating part inside the stator, connected to the motor shaft. As the magnetic field from the stator interacts with the rotor, it causes the rotor to turn. In DC motors, a commutator and brushes help switch current direction, keeping the rotor spinning. Bearings reduce friction and support the rotating shaft, while the housing protects the internal components. These components work together to efficiently produce motion, making electric motors essential in countless applications, from household appliances to industrial machinery and electric vehicles. 9. What is the difference between generator and inverter? A generator and an inverter both supply electrical power, but they operate differently and serve different purposes. A generator converts mechanical energy into electrical energy using fuel like diesel, petrol, or gas. It is ideal for producing large amounts of power during outages and is commonly used in homes, businesses, and industries. An inverter, on the other hand, converts DC, direct current, into AC, alternating current. It doesn't generate power but uses stored energy from batteries or solar panels. Inverters are quieter, more eco-friendly, and suitable for low to medium power backup. The key difference is that generators create power, while inverters convert and deliver stored power. Generators are used for extended power supply needs, while inverters are preferred for short-term, clean, and efficient power backup in homes or offices. 10. Explain the concept of three-phase power. Three-phase power is a method of electric power generation, transmission, and distribution that uses three alternating currents, each set 120 degrees apart in phase. Unlike single-phase power, which delivers power through one conductor, three-phase power uses three live wires, and often a neutral, to deliver a constant and balanced power flow. This setup ensures smoother and more efficient operation of heavy electrical equipment. Three-phase systems are commonly used in industrial and commercial settings because they provide higher power capacity, reduce energy losses, and allow for smaller, more efficient motors and transformers. It also improves the reliability and stability of the electrical supply. Because of its ability to deliver more power using less conductor material, three-phase power is ideal for large-scale applications and essential for powering high-demand machinery, elevators, and HVAC systems. 11. What is the role of a capacitor in a circuit? A capacitor is a passive electronic component that stores and releases electrical energy in a circuit. It consists of two conductive plates separated by an insulating material called a dielectric. When voltage is applied, the capacitor accumulates electric charge on its plates, creating an electric field. In circuits, capacitors serve several important roles. They are used to smooth voltage fluctuations, especially in power supplies, by filtering out noise or ripples. In timing circuits, capacitors control the delay or frequency. In AC circuits, they can block direct current while allowing alternating current to pass, acting as coupling or decoupling devices. Capacitors also improve the power factor in inductive loads and help stabilize voltage and power flow in complex systems. Their ability to quickly charge and discharge makes them essential for modern electronics and energy management. 12. Why are star and delta connections used? Star and delta connections are used in three-phase electrical systems to manage voltage, current, and power distribution effectively, especially in motors and transformers. In a star-Y connection, one end of each of the three windings is connected to form a neutral point, while the other ends are connected to the power supply. This setup provides two voltage levels, line and phase voltage, making it suitable for long-distance power transmission due to reduced current and lower losses. In a delta connection, the ends of each winding are connected in a closed loop, forming a triangle. This provides higher current and torque, making it ideal for heavy machinery and industrial loads. Star-delta starters are often used to reduce the starting current of motors, enhancing efficiency and protecting equipment from damage during startup. 13. What is grounding and why is it necessary? Grounding, also known as earthing, is the process of connecting electrical systems or equipment to the earth using a low-resistance wire. This provides a safe path for excess or fault current to flow directly into the ground, preventing electrical shock, fire, or damage to equipment. Grounding is essential for safety and system stability. In the event of a short circuit, lightning strike, or insulation failure, grounding ensures that dangerous voltages do not build up on exposed metal parts. It also helps stabilize voltage levels by providing a common reference point for electrical systems. Without proper grounding, people and equipment are at greater risk of electric shock, system malfunctions, and equipment failures. Grounding is a critical safety feature in residential, commercial, and industrial electrical installations, ensuring protection and proper operation of electrical systems. 14. What is a relay and how does it work? A relay is an electromechanical or electronic switching device used to control a high-power circuit using a low-power signal. It works like a switch but is operated electrically, not manually. A typical relay consists of an electromagnet, coil, armature, spring, and contacts. When a small current flows through the coil, it generates a magnetic field that attracts the armature, causing it to move and close or open the connected contacts. This action either completes or interrupts the circuit being controlled. Relays are widely used in automotive systems, industrial automation, home appliances, and control panels to isolate and control different voltage levels. They enable safe and efficient control of multiple devices from a single point. Relays provide flexibility, protection, and automation in electrical systems, making them essential components in modern electrical and electronic applications. 15. How do you ensure electrical safety in a project? Ensuring electrical safety in a project involves following strict guidelines, standards, and best practices to protect people, equipment, and property. The first step is conducting a thorough risk assessment to identify potential hazards. Use proper personal protective equipment, PPE, like insulated gloves, safety boots, and eye protection. All electrical installations should follow recognized codes, such as the NEC or IEC standards, and must be done by qualified personnel. Always turn off power before working on any circuit and verify it with a tester. Use circuit breakers, fuses, grounding, and insulation to prevent overloads and short circuits. Proper labeling, warning signs, and lockout, tagout, LOTO, procedures should be in place. Regular inspections and maintenance ensure continued safety. Training workers on electrical hazards and emergency response also plays a key role in maintaining a safe work environment. 16. What are the common causes of power failure? Power failures, also known as blackouts or outages, can occur due to various technical and environmental reasons. One of the most common causes is weather-related issues, such as storms, lightning, floods, or high winds that damage power lines and equipment. Equipment failure, including transformer or circuit breaker malfunctions, can also lead to outages. Overloading the power grid, especially during peak demand times, can cause system instability and blackouts. Fallen trees, animals interfering with electrical infrastructure, or vehicle accidents that damage poles and wires are other frequent causes. Human error during maintenance or construction work, and planned outages for upgrades or repairs, also result in temporary power loss. In some regions, poor infrastructure or fuel supply issues at power plants contribute to frequent failures. Preventive maintenance and modernization can reduce such disruptions. 17. How do you test electrical equipment for reliability? Testing electrical equipment for reliability involves a series of procedures to ensure the device performs consistently under normal and extreme conditions. The process starts with visual inspection to identify any physical damage, loose connections, or worn-out parts. Insulation resistance testing checks for leaks or breakdowns in insulation using a megometer. Continuity tests ensure proper connections and verify circuit integrity. Load testing involves operating the equipment under expected or increased loads to assess performance and thermal stability. High voltage testing, HIPOT, helps detect weaknesses in insulation under stress. Thermal imaging can reveal overheating components. Functional tests check if the device operates according to its specifications. Scheduled preventive maintenance and data logging over time also help identify reliability trends. Thorough testing ensures safety, extends equipment life, and minimizes unexpected failures in electrical systems. 18. What software tools are you proficient in? I am proficient in a variety of software tools commonly used in electrical engineering and technical fields. These include AutoCAD and AutoCAD Electrical for designing and drafting electrical schematics and layouts. I also use ETAP and EPLAN for power system analysis, load flow studies, and panel design. For circuit simulation and analysis, I'm experienced with Proteus, Multisim, and PSpice, which help in testing and validating electronic circuits before actual implementation. I also work with MATLAB, Simulink for modeling, simulations, and control system design. In project documentation and reporting, I regularly use Microsoft Office tools like Word, Excel, and PowerPoint. For project management, I'm familiar with Primavera and MS Project. These tools allow me to design, simulate, analyze, and manage electrical projects efficiently and accurately. 19. Tell me about a challenging electrical project you worked on. One of the most challenging electrical projects I worked on involved designing and implementing a power distribution system for a mid-sized manufacturing plant. The challenge was to ensure uninterrupted power supply while accommodating both heavy machinery and sensitive control equipment. I began by conducting a thorough load analysis and developed a layout using AutoCAD Electrical. The system required both star and delta motor connections, along with backup power integration using a generator and an inverter. Coordinating with civil and mechanical teams while staying within the timeline and budget was demanding. I used ETAP for short circuit and protection coordination studies and ensured compliance with safety standards. Despite unexpected delays due to supply chain issues, the project was successfully completed and is now running efficiently. It greatly enhanced my skills in problem solving and teamwork under pressure. 20. Why should we hire you as an electrical engineer? You should hire me as an electrical engineer because I bring a strong combination of technical expertise, practical experience, and problem-solving skills. I am proficient in industry-standard software like AutoCAD, ETAP, and MATLAB, and have hands-on experience in designing, analyzing, and troubleshooting electrical systems. I approach every project with attention to detail, safety, and efficiency, ensuring compliance with industry standards and project requirements. I've successfully managed challenging projects, working under pressure and collaborating effectively with cross-functional teams. I'm also committed to continuous learning, staying updated with emerging technologies and best practices in the electrical field. My passion for innovation and drive to deliver high-quality results make me a valuable addition to your team. I'm ready to contribute my skills to help achieve your company's goals and ensure the success of your engineering projects. Thanks for watching. If you found these questions helpful, like, share, and subscribe for more career tips. Comment below which question you struggle with most. Let's help each other succeed.